All right, next up, we have Rohin talking about the Alexsevsky Conjecture in 9 and 10 dimensions. Thank you very much. And I'll give you a warning, same kind of time, about 5 to 11, and then we'll go into breakout rooms and go from there. Thanks very much.
All right, great. Thank you. So as the title suggests, I'm going to be talking to you today about the Alexevsky Conjecture in 9 and 10 dimensions. To give you a bit of an idea about sort of what we're going to be talking about to begin with, I want to sort of motivate sort of the idea behind sort of why one would be interested in studying the Alexevsky conjecture in general, from the point of view of just pure Riemannian geometry. From there, I'm sort of going to give you an idea about sort of where we come in and where we sort of came up with the strategy of developing this solution to the 9 and 10 dimensional cases of this. It sort of essentially breaks up into two parts. Part one, a classification, which is purely algebraic, and part two, which is resolving the conjecture, which uses a lot more geometry. And then right at the end, I'm just going to give you a sort of an idea about sort of where we sit at the moment with regards to this conjecture. So this conjecture sort of arises from studying the problem, given a smooth manifold, can we find a metric which is best adapted to the geometry of the manifold? And so, well, what do I mean by best adapted? I could mean any number of things. In the case that we're sort of interested in, we mean sort of constant curvature. And now, well, we have to sort of define exactly what we mean by constant curvature in this case as well. We could, for example, mean constant scalar curvature. We could mean constant Ricci curvature, constant Riemannian curvature, and any myriad of other curvatures that one might be interested in. For example, if one studies the constant scalar curvature manifolds, one attains the sort of the well-known classification result that says, well, if we have a Riemannian manifold which has a complete Riemannian manifold which has constant curvature, then it is locally isometric to one of these space forms. And these space forms are classified by either hyperbolic, Euclidean, or spherical geometry, respectively. And so what one does is they can go one step further and say, well, what happens if we chose a different type of curvature, say Ricci curvature? And in the case, well, where we're looking at constant Ricci curvature manifolds, we call these manifolds Einstein. And so I've just written this definition down here. A Riemannian manifold is called Einstein if it satisfies this Einstein equation, that the Ricci curvature is constant, constant scalar multiple of lambda. And so what the goal here really is to understand the geometry and the topology of these sorts of manifolds which satisfy the Einstein equation. Unfortunately, it's a non-linear second-order partial differential equation, and there are no general sort of existence results to this equation. And so how do we get around this? The solution is really to impose sort of symmetry assumptions, to assume that your manifold is, for example, symmetric, or to assume your manifold is homogeneous, and other things as well. For those of you who haven't heard what a homogeneous manifold is, we're just going to define it here as the sort of the quotient space of some Lie group by some closed subgroup. So the data here really is you have a Lie group and you have some closed subgroup, and this defines a smooth quotient. We also have an action of G on this quotient space. We also have an action of G on this quotient space, and we can assign sort of a Riemannian metric to these homogeneous spaces which respect this group action G. In other words, this group action acts by isometries, we say. And now, sort of in the homogeneous case, Einstein metrics, the results on Einstein metrics really depend on the sign of the Einstein constant lambda here. And so if the Einstein constant is positive, we find that these manifolds are actually all compact by the Bonnet-Myers theorem. In fact, they also have finite fundamental group. In the case where we have a Ricci flat manifold, these manifolds also turn out to be flat. And again, and finally, I guess, in the negative case, all that's really known at the moment is that these manifolds are actually just non-compact. And so in this non-compact setting, this sort of leaves much to be desired, right? So we still have this sort of unresolved major problem called the Alexevsky conjecture, which was conjectured in 1975 by Alexsevsky. it states every connected homogeneous Einstein manifold with negative Ricci curvature is actually diffeomorphic to Euclidean space. And this provides us a very sort of strong topological constraint on non-compact homogeneous Einstein spaces. That is that they are all contractible. And so perhaps at least from the topological point of view, one might be interested in studying this conjecture. And also from the geometric point of view, it provides very strong conditions on the space of these invariant metrics. So far, at least, we've seen sort of major steps in trying to understand this conjecture in sort of lower dimensional cases and also in some general cases. For an example of a general case, if our manifold is symmetric, in other words, this H is sort of maximal compact sitting inside of G, then actually this space is diffeomorphic to a solved manifold, which is again diffeomorphic to Euclidean space. In dimensions at most 8, this problem is essentially resolved in but a few cases, and these cases are all Lie groups. And also in 9 and 10 dimensional space, the results depend significantly on whether or not our group G is unimodular or non-unimodular. In the non-unimodular case, at least, this problem is resolved by Arroyo and Lafuente in 2016. So what does this leave us with? This leaves us with some cases in lower than 8 dimensions, but in particular in 9 and 10 dimensions, this leaves us with the case where our group G was unimodular. And some results say that this G is actually also semi-simple. And some structural results also allow us to assume that this G actually also contains no compact simple factors. So if one decomposes this group into its product of simple factors, we find that none of these things are going to be compact. And this actually helps us with our classification result later on. And so, well, what do we do in order to try and verify the conjecture in 9 and 10 dimensions? The problem really breaks down into 2 steps. The first of these steps is to sort of understand non-compact 9 and 10 dimensional homogeneous spaces which aren't diffeomorphic to Euclidean space. That is, if we have a homogeneous space which is diffeomorphic to Euclidean space, it automatically satisfies the conditions of the conjecture, so we can neglect it. So again, we can assume G is semi-simple without compact simple factors. We also assume that the homogeneous space is non-symmetric. This is because all of these symmetric spaces are going to be diffeomorphic to Euclidean space. And then the problem really is, once one understands all of these homogeneous spaces, to show non-existence of solutions to the Einstein equation in all of the cases that we classify. And so how does one do this? One does this by first understanding the space of invariant metrics on these homogeneous spaces, and they use formulas for the Ricci curvature. And this really allows us to sort of write algebraic equations to test the existence of Einstein metrics on these spaces. So breaking now into the first step, what we need to do is provide a list of non-compact homogeneous spaces whose simple factors are all, well, who breaks up into simple factors, so semi-simple. Again, assume each of these Gi are non-compact, assume the space is non-symmetric. We can also use this main geometric tool that we proved in our paper, which says that if this homogeneous space is Einstein, then in fact, none of these factors can be isomorphic to SL2R. And so what this really does is it allows us to essentially cut out half of the cases. And this sort of is the main step forward from what we were doing in the past, where now we can disregard essentially half of the cases that we would have had to include had we not had this result. And so this problem of finding non-compact homogeneous spaces with semi-simple transitive group essentially boils down to finding subalgebras of non-compact semi-simple Lie algebras. Non-compact in the sense of the Lie group associated to these Lie algebras is non-compact. And so this problem, unsurprisingly, is quite hard. We have sort of none of the tools that really aids classification results in the compact setting. And so what one does is they sort of think, well, maybe I can solve this problem if instead of having non-compact, I had compact. And in fact, yes, this problem is a lot easier to solve. And so we already have lists of low dimensional cases. We have general classification results that we can use as well. And maybe unsurprisingly here, the fact that I'm sort of jumping between compact and non-compact, maybe if you've heard of the duality of symmetric spaces before, irreducible symmetric spaces of the compact and non-compact types, then you'll see sort of where this is going. Because, well, there is actually also a partial duality between the problems of finding subalgebras of non-compact semi-simple Lie algebras and finding subalgebras of compact semi-simple Lie algebras. And so what one does is they think about the problem in terms of the simple case. So I've just written out that you can sort of break these up into all of their simple factors. Assume for a minute that these things are actually just simple. What one can do is, if you start with a compact, simple, homogeneous space and consider its isotropy subalgebra, think for a minute finding all of the maximal subalgebras K, which contain this subalgebra H. And so if this G modulo K is a symmetric space or a symmetric pair, is an irreducible symmetric space of the compact type rather, you can use this duality idea between compact and non-compact symmetric spaces to dualize your irreducible symmetric space of the compact type, which you've just generated by considering a maximal subalgebra, into a symmetric space of the non-compact type. And so this duality procedure also respects some sort of isomorphism between these Lie algebras at the Lie algebra level. And you can use this in order to give you sort of a homogeneous space without compact simple factors. And so if you take all maximal subalgebras, this actually gives you a complete list of non-compact semi-simple homogeneous spaces. And I've just sort of provided a short little example here. What we do is we start with, for an example, SO5 modulo SO3. This actually has, this H here, SO3, actually has two sort of maximal subalgebras. One of these is SO4, the other is SO3 cross SO2. These two spaces here are actually symmetric spaces. And so we can use the duality between compact type and non-compact type symmetric spaces in order to give us non-compact irreducible symmetric spaces, which again, we have SO4, SO3 cross SO2. This contains an SO3 subalgebra. And so this guy here and this guy here gives us two duals to this homogeneous space SO5 modulo SO3. And so what we get is this not exactly a duality between these compact and non-compact type homogeneous spaces, but in a sense, an injection from the compact type to the non-compact type. And if we know enough about these maximal subalgebras, then we can recover a complete list of these non-compact type homogeneous spaces. And so, well, we did the work for this, and we came up with the following list. As you can see, a brief overview of the list. We have the compact type homogeneous spaces here, the symmetric, I guess, completions, and then the non-compact duals in this third column here. And then, well, finally here, I just want to bring your attention to this isotropy representation stuff that we've written here. Essentially, what this does is it provides sort of an algebraic condition on each of these spaces, which we'll return to later, which allows us to sort of classify these, classify the space of invariant metrics on these homogeneous spaces. And I guess the important cases that I want to detail to you are the cases where we have a QI isomorphic to a PI. All of these other ones here, you can sort of not worry about. You can sort of sweep it under the rug for now. But if you see a QI and a PI, these are the ones that we really want to pay attention to. So the second example here is exactly what I'm talking about, but not the first example. So now we have a list of all of the spaces that we need to cover for our conjecture. And so the goal here now really is to show non-existence of Einstein metrics of all examples on the list. The issue being, this problem I highlighted earlier is quite hard to solve because it's a nonlinear second order partial differential equation. Fortunately for us, our symmetry assumptions come into head here in the sense that, well, if we're looking at the space of G invariant metrics, these are actually equivalent to endomorphisms which compute on this reductive complement P plus Q here. And so what we get is, well, if we use formulas for the Ricci curvature and homogeneous spaces, we use this identification here, then we can actually turn this PDE just into an algebraic equation. And this is sort of really tractable for computers, right? So we can sort of if we're lucky enough, we can shoehorn this into a computer, and we can hope that, well, the computer can say, yes, there are solutions, or no, there aren't any solutions. And then just to mention here as well, this condition that I mentioned earlier, if we have pi isomorphic to qi for one of these elements in this list here, for example, number 2 here, then we have to consider the space. Then we have to consider this space in one of our examples. But if this never occurs, if we always get pi non-isomorphic to qi for each I and j, then actually these spaces admit no invariant metrics, or no invariant Einstein metrics. And so what this really does is it says you can ignore number 1, you can ignore 3, and so on and so forth. Okay. So essentially, we're left with very few cases. And these very few cases we can check directly. To give you an idea, I'm just going to go over a quick example. If we take the homogeneous space SLN plus 1 over SON, this has maximal compact subgroup SON plus 1. The isotropy representation decomposes as this guy here. And the important thing to notice with this is that we have P1 isomorphic to Q1 here. This Q1 and this P1 sitting here. These representations are equivalent to each other because they are just the standard representation. Rn.
I think you cut out for a little bit there.
Have I cut out? Where did I stop?
Something, these representations, and then Rn.
Ah, yes, okay. So coming back, so these representations are equivalent. So these form cases that we do need to check. These representations are equivalent because they are just the standard representations of SON on Rn. In fact, we can simplify our case a little bit more just for the sake of having a simpler computation. In the case where n equals 2, the dimension of this homogeneous space is 7, so it's not actually one of the cases that we looked at in our paper, but the computations do again simplify greatly. And well, what we find is that we can decompose the space of SL3R invariant metrics on this guy here in this form here. And sort of the important part to note is that for every SL3R invariant metric, we have that P0, Q1 plus P1 and P2 are always going to be orthogonal to each other. And so this is sort of one of the major observations that allows us to sort of try and reduce these metrics. In order to try and prove that there aren't any Einstein metrics on these homogeneous spaces. In fact, just for the sake of computation, one can prove that, well, the Ricci curvature in off-diagonal terms in some orthonormal basis, which again swept under the rug, is given by this guy here. And well, one should expect that if you have an Einstein metric in an orthonormal basis, this off-diagonal Ricci curvature term should vanish. And so if one can prove this vanishes under certain conditions, one can prove non-existence of these solutions to Einstein metrics. And so the goal again is just to prove non-existence of solutions in all of the cases that we've mentioned that do not satisfy certain conditions of certain theorems. And so, well,
5 minutes.
Sure. And so, well, we can give this our best shot possible. And sort of this is sort of where we got to with it. We were able to show that in the case where our homogeneous space is not given by one of these, I guess, 6 possible exceptions, then our manifold has to actually be diffeomorphic to Euclidean space. So I guess an important thing to mention here is, apart from this first case, SP11 modulo U1, all of these cases are left invariant metrics on Lie groups. And so what one sort of understands if they do this enough is that in the case where you have a Lie group or something with small isotropy, in the case here where we have a one-dimensional isotropy, the space of invariant metrics is actually quite large. Why is this the case? Well, you could think, well, having a small isotropy or having no isotropy at all means that we can't reduce some of these factors here all the time. And I guess, well, a natural question is, maybe you thought of this right at the start, why only 10 dimensions? Why not 11 dimensions? Why not 12 dimensions? Why not continue on as far as you want, right? The main reason for me, at least, is we don't actually have any results for the non-union modular case in higher dimensional examples like 11 dimensions, 12 dimensions, and so on and so forth. So how does this hinder us? Well, in 11 dimensions, we already have examples like this guy here. And well, the important thing about this guy here is that the Einstein equation reduces to an equation for left invariant metrics on SL2C. And well, already here we can see that SL2C is something that we haven't even been able to cover in its specific case yet. So this sort of forms a major sort of obstruction to trying to move the conjecture up to 11 and 12, so on and so forth dimensions. Sort of the main goal would be surely to try and kick off some of these Lie group cases to begin with. One also finds that you can attain new examples of homogeneous spaces with small isotropy as you get into higher dimensions. And this again forms, I guess, maybe sort of a moral barrier between moving this conjecture up into higher dimensions. Because if you have a homogeneous space with small isotropy, again, these spaces admit very complicated spaces of invariant metrics, which can hinder our results massively. Anyway, I think I will leave it there. Thank you.
Thank you so much.
I think I should also say, so I did say various authors at some point along the presentation. So just to give them homage, here are the papers of other people who've also been working on this conjecture. If you're interested, please give them a look because they're very good.
Awesome. Thanks so much. Does anyone have any questions? I sadly forgot to make everyone a co-host, so I'll wildly do that now because I got distracted by the talk. No one.
Yeah, I've got a question.
Go for it.
Oh. I guess this is a more philosophical question. To me, a homogeneous space tends to mean just a space with a transitive isometry group, right? Like I don't put any sort of assume it's a Lie group. So in particular, I think a lot about hyperbolic manifolds, and they're things with what I think of as negative curvature, and they're certainly not all Rn, like contractible.
Yes.
Can you tell me a bit about you're using this Lie group definition? Can you tell me a bit about the motivation for using that instead, or what's going on there?
Yeah. So these definitions between transitive action of some Lie group on homogeneous space and Lie group modulo some other cosets, some other Lie subgroup, these definitions are actually equivalent to each other. Perhaps you know this. So the distinction between using one or the other in this case is purely sort of, I guess one looks perhaps a little bit nicer in presentation format at this point. Because in order to define a homogeneous space, I don't have to define transitive action, has to act isometrically, so on and so forth.
Could I rephrase the question then?
Yes, go for it.
Why aren't hyperbolic 3 manifolds a counterexample to this conjecture?
Why aren't hyperbolic 3 manifolds a counterexample to this conjecture?
They are locally homogeneous, not globally homogeneous. Sorry to interrupt, Rohin, but they are only locally homogeneous, right? No global action. Only the universal cover, which is hyperbolic 3 space, but that one is diffeomorphic to R3, right? So
yeah,
that's
sure,
a good
thanks.
question. It's a good question. Lots of symmetries, but only local symmetries.
Thank you, remember.
I had a question.
Yes, go for it.
So in the slide where you explicitly computed reach 2, 4 or something, right?
Yes.
So is your claim that can't be 0? Is that your claim?
The claim that you would want to have is that this curvature equals 0 if and only if E is equal to 0.
And that would tell you that there's no Einstein metrics?
Yes.
Because these G's aren't diagonal, so I guess it's not completely clear to me. I guess not. Anyway, yeah, cool. Thanks.
Sure.
Cool. If there's no other questions right now, we'll thank Rohin again for his great talk. I will create some breakout rooms. If you want to do a max exodus, do so now so I can create the right number. I think at this point I'll do 3 breakout rooms and then go from there. Again, thank you so much.